So we are continuing to go deeper in our understanding of the step response of underdamped second order systems. And now I want to talk about how that relates to pole locations. Pole locations get controls professors really excited. Pole locations are a very big deal. Pole locations tell us a lot about a system and how it's going to respond to various inputs, be they step, impulse, or sine wave of various frequencies. And as the frequencies change, the pole locations tell me how the system is going to respond. So dynamic systems and controls engineers think in terms of pole locations. This is just a really important foundational thing. So I think that leaves us with three key questions. What are pole locations? In case we haven't been clear on that, I want to be clear on that now. How do pole locations relate to zeta, omega n, and omega d? And then, probably not going to get to this in this video, but how do pole locations affect the step response? So, in terms of definition, what are pole locations? When we say poles, we mean the roots of the denominator of a transfer function. So if I set my denominator equal to 0, what are the values of s that make that equation true? Or what are the values of s that cause the denominator to go to 0? What are the roots of setting the denominator equal to 0? I think those are all equivalent ways of saying the same thing. So if we have this underdamped second order standard form and we want to find its poles, we take this denominator, set it equal to 0, and then use the quadratic formula to find the roots of that equation. So let me do that on my DocCam now. So I have a transfer function and I want to find its poles. If these were all hard numbers, I could just use my calculator or Python. If it were higher order, I would have to do something like that. Because the underdamped second order transfer function is so important, we want to do this one symbolically so we can talk about how zeta and omega n relate to the pole locations, and we know how zeta and omega n relate to the step response, so that'll be important. So if I just set s squared plus 2 zeta omega ns plus omega n squared, set my denominator equal to 0, the s values that make that true, the s values that cause the denominator to go to 0, are my poles. So I'm now in the perfect form to use my quadratic formula. So s is going to be, so this is my b, c, and a from high school, right? So we remember that it's a negative b plus or minus the square root of b squared minus 4ac all over 2a. And so we're substituting in a is equal to 1, b is equal to 2 zeta omega n, and c is equal to omega n squared. And if it made you feel any better, x is now s in a full high school conversion. So we're talking about a negative 2 zeta omega n plus or minus the square root 4 zeta squared omega n squared minus 4 omega n squared over 2. And I can clean up what's going on inside this radical. It's like a weird 2 zeta combination that makes it look like a 3. So I'm going to factor out a 4 omega n squared times zeta squared minus 1 over 2. And then if I take this term, 4 omega n squared, and bring it outside the square root, I'm going to end up with 2 omega n. So s is equal to a negative 2 zeta omega n plus or minus 2 omega n. And then I'll be left with the square root of zeta squared minus 1 divided by 2. So I can get a 2 out of everything. And so I've got s is equal to negative zeta omega n plus or minus omega n zeta squared minus 1 square root. Now if I know that zeta is greater than 0 but less than 1, then this term is going to be negative. So I'm going to factor out a negative 1 still inside the square root. But then I can take this negative 1 and pull it outside, and the square root of a negative 1 is just going to be our imaginary number. think I've said this before, I use J instead of I, because I, in my mind, is for current. And I was missing a closed parenthesis there. So negative zeta omega n plus or minus the square root of j omega n times the square root of 1 minus zeta squared. But you hopefully recognize from a previous video that we've defined this to just be omega d because it comes up so often. So our ultimate conclusion here is that the roots, or the poles, of our underdamped second order transfer function, the roots of its denominator, are negative zeta omega n plus or minus j omega d, which can also be written as, the book is kind of funny about this sometimes. So sometimes I'll call it zeta omega n, and sometimes the book will call it sigma. And so know that those are, so we're saying this, but we're defining sigma to be the zeta omega n product, and we're defining omega d to be omega n square root of 1 minus zeta squared. So those are the poles or roots. Sorry, my exposure got really weird there. I think it's a cloudy day and the sun is kind of coming and going on me just a little bit. So these are the poles of omega n squared over s squared plus 2 zeta omega n s plus omega n squared. And so we want to talk, coming up soon, we're going to plot those poles graphically because that will turn out to be helpful. We want to understand how do those pole locations relate to what we know about our step response, right? Which is e to the negative sigma t cosine omega dt. Sometimes my mind runs ahead while I'm trying to write. Pretty sure this is sigma over omega d, although I've been very non-committal about that. So, as my pole locations change, it changes zeta omega n and omega d depending on, so in root locus, for example, we're going to adjust our control gains, which is actually going to move the poles of our closed loop system, or maybe we have some kind of control over the system that we're designing. How would the pole locations affect the step response? Or we're just trying to compare two systems. And if we know they have different pole locations, how do their step responses compare? What's going to ultimately boil down to, okay, how is the zeta, omega n, omega d different or similar between the two? And then plug those things in as appropriate. What happens?